Hi, welcome back to Moose in Chemistry. This is electron configuration of the element zinc, Zn. When we look on the periodic table, zinc is number 30, right? So it's going to have an atomic number 30. Its atomic mass unit is going to be 65. So since the atomic number is 30, that means we have 30 protons in the nucleus. And since zinc is electrically neutral, we're going to have 30 electrons also. Well, now, what about the neutrons? Well, to get the neutrons, if you remember, you take AMU minus protons equals the number of neutrons. Pretty darn cool, huh? So you would go 65 minus 30, right? And give me 35 neutrons. Wow, that's just awesome. So now, we are ready to go to our electron configuration. But before we do, we really should look at our subshells. Our S subshell can hold 2 electrons. Our P subshell can hold 6 electrons. Our D subshell can hold 10 electrons. And our F subshell, well, that can hold 14 electrons. We're going to use the off-ball principle, which states that we should fill the lower energy levels first before we fill the upper energy levels. And we're going to use something called the diagonal rule. Here's your diagonal rule. Start with the 1s going down, so we're going to go 1s2. Pretty darn snarly, huh? 2s2. Cool. 2p6 and then 3s2. It's going pretty good. 3p6 and 4s2. And then all we need left is 10 more electrons, and that 3d shell takes care of those. So it's 3d10. Awesome. Now, let's look at orbital notation. That deals with Hund's rule. Basically, what Hund's rule states is that in every suborbit, you have to put an up arrow before you put the down arrow. So like in the case of 1s, you just go up and down. Same thing with 2s, up and down. But here's a really good explanation of Hund's rule. Look at this 2px, 2py, 2pc. Now watch what I do. Go up, up, up. Now you put a up arrow in every suborbit. Now we can do the down arrow. See that? Pretty darn cool. You just keep repeating that. So go up and down. Again, up, 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 and then down, down, down. 4s, up, and then down. Then 3d x squared minus y squared, 3d xy, 3d yz, 3d xz, and 3d z squared. Up, 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 and then up, and then of course down and down. Pretty amazing, huh? So now let's look at our noble gas notation. What's the nearest noble gas to the element zinc? Well, of course it's argon, right? So we put Ar in there. And now look at our valence shell right here. It starts with the 4s, and we block that in. Then we're going to write it numerically in order down here. 3d10, 4s2. Man, that is so awesome. Now, remember that it's in the D block, zinc is. So you're going to have n minus 1, right? So now, what are you going to do? You think it's 4, but it's not. It's going to be 4 minus 1 is going to be 3. So our n value is 3. Principal quantum number is 3. It's in the D block, so it's going to have a 2 for the angular momentum number. And when we repeat this pattern for our magnetic number, minus 2 minus 1, 0, 1, 2, that's 5. Minus 2 minus 1, 0, 1, 2. It's the last element on the D block, right? On that particular period. So then we're going to circle the 2 there, right? So we're going to put a 2 there. And our last arrow, which is located right. Think about this, guys. It's going down, right? So our spin value, S number, is going to be 1/2 negative. And that takes care of Pauli's exclusionary principle, which states that no two elements can have the same set of quantum numbers. Well, listen, you guys be snarly, and we'll see you back here at Moose in Chemistry.